Welcome to Lecture 27, in which we will discuss the Quine-McCluskey method. In the near future, we will be trying to construct quantum circuits to realize functions in an efficient way. And one of the first steps for doing that is to start with an efficient classical circuit for implementing the same function. And one way in which to write an expression or construct a circuit in an efficient way for the classical case is to use something called the Quine-McCluskey method. So let me illustrate this by an example. So what we'll say is the following. Suppose f of w, x, y, z is equal to the following. We'll have w prime, x prime, y prime, z prime, or w prime, x prime, y, z prime, or w prime, x, y prime, z, or w, x prime, y prime, z prime, or w, x prime, y prime, z, or wx prime, y, z prime, or wx, y prime, z, or wx, y, z prime, or wxyz. So suppose we had a function of the four Boolean variables w, x, y, and z that was equal to this expression, and we wanted to in some way write this more efficiently. And I won't get into all the details of exactly what it is that we're minimizing quite yet, but we want to simplify this as much as possible before trying to actually implement it in hardware. And so one of the ways that we can simplify a function is called the Quine-McCluskey method. Now, some of you may be familiar with something called the Carnot-Mappe method, and it certainly will work in this case as well. The only objection to the Carnot-Mappe method is that it's only suitable for functions up to 5 variables, and we would like something that's appropriate for functions of possibly more variables than that. So we'll go with the Quine-McCluskey method. Furthermore, the Quine-McCluskey method is easily programmed on a computer. So what I'm going to show now is the details of the Quine-McCluskey method for simplifying a function, and then for your in-lecture problem, we'll give you another function for which you will apply this same method to assure that you understand it. So the first step here, will be to write down a binary number representing each term. Now, again, I don't want to go into too many details with this problem. because we could spend considerably more than one lecture on this. But I will point out that each one of these terms has all of the independent variables in it in either primed or unprimed form. This expression that we have is called a min-term realization of the function. Each one of these is called a min-term, again, because each one of the variables is present in it. For instance, if we had the first term was x prime y prime z prime instead of w prime x prime y prime z prime, that would not be a min-term. A min-term has to have all of the variables present. And so really, even prior to this first step, you want to make sure that your function is expressed as a sum of min-terms. And if you have some terms that are not min-terms, you can get min-terms from those by ANDing the expression with 1 written in a convenient fashion. For instance, but just as a quick example, suppose that the first term had been x prime y prime z instead of w prime x prime y prime z. Prime z prime. So suppose that the first term had been x prime y prime z prime instead of w prime x prime y prime z prime. Then in that case, we would not have been ready to start yet, because we need to get the function expressed as a sum of min-terms, and this x prime y prime z prime is not a min-term because it does not contain all of the independent variables of the problem. However, we could convert it to a min-term by ANDing it with 1 written in a particular way. What I mean by that is the following. One can be written as w or w prime. And of course, 1 ANDed with x prime y prime z prime is the same as x prime y prime z prime. So by ANDing this expression with w or w prime, I have not changed the value of it. And then when I multiply this out, I'll get w x prime y prime z prime, or w prime x prime y prime z prime. So this term, x prime y prime z prime, is actually equal to the sum of these two terms. And notice that both of these are indeed min-terms, because each of these has all of the independent variables present. So if you have a situation, I don't expect that you will, because I'll be making up these problems and there's no need in adding this extra complication. But if you ever in the future, let's say, want to simplify something that for which the original expression is not all min-terms, then you can go to any term that's not a min-term and pull this trick, this kind of a trick. Now, this is what you do if w is the missing variable. Let's say if x were the missing variable, then you would AND it with x or x prime. If y were the missing variable, you would AND it with y or y prime, and so on, to get your min-terms. So that's what you would do. But fortunately, we don't have to worry with any of that in this case, because all of these are min-terms. So now we write down this binary number representing each term, and the way that those binary numbers are determined is simply to assign a 0 to any variable that is primed and a 1 to any variable that's unprimed. So the first term is represented then, since all the variables are primed, is represented by 0, 0, 0, 0. The second one would be 0, 0, 1, 0, and then the next one would be 0, 1, 0, 1. The next one would be 1, 0, 0, 0. The next one is 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, and then finally 1, 1, 1, 1. So now we collect all of those numbers together. So let's do that. We have 0, 0, 0, 0, but we're going to, let's say, collect these binary numbers according to the number of zeros in each of them. Okay, so what I mean by that is we start by listing the terms with no zeros. And of course, there's only one of those that has no zeros, and that is 0, 0, 0, 0. And that's it. So we've now accounted for the first one. Now let's list all terms that have 1 0. Well, 0, 0, 1, 0 is one of those. And 1, 0, 0, 0 is another one. And those are the only two that have 1 0. And let me also, while I'm at it, let's just go ahead and write down beside each of these the term that it corresponds to. So 0, 0, 0, 0 corresponds to that first term, W prime, X prime, Y prime, Z prime. 0, 0, 1, 0 corresponds to W prime, X prime, Y, Z prime. 1, 0, 0, 0 corresponds to W, X prime, Y prime, Z prime. And at the same time, let me do one other thing also. I'm going to go up to our list and cross off the terms as we write down each. So we've taken care of this first term, and we've taken care of this term, and we have also taken care of this term. Okay, and now that's all the terms with 1 0. So now let's look at terms with 2 zeros. Okay, well, the 0, 1, 0, 1 term is an example. 0, 1, 0, 1. And that is W prime X, Y prime Z. W prime X, Y prime Z. So we'll come and cross that term off. The W X prime Y prime Z is another. That's 1 0 0 1. 1 0 0 1. And that's W X prime Y prime Z. W X prime Y prime Z. And we cross that off. 1 0 1 0 is still another example. 1 0 1 0, and that's W X prime Y Z prime. W X prime Y Z prime. And that's all the terms with 2 zeros. Now we look at the terms with 3 zeros. And there are 2 of those up above. There's 1 1 0 1, 1 1 0 1, which is W X Y prime Z, W X Y prime Z. So we cross that off. And then 1 1 1 0 is another 1 1 1 0, and that's W X Y Z prime. W X Y Z prime. So we cross that off, and then finally I'm counting this down wrong. You were probably wondering. This is. Let's. Okay, sorry about that. I guess I was on autopilot, because what I should have said here, everything has been done correctly. I just didn't label it correctly. You're collecting these numbers according not to the number of zeros, but according to the number of ones. So no ones, and then 1, 1, 2 ones, oops, 3 ones, and then we write down finally there's only one term with 4 ones, and that's 1, 1, 1, 1, 1, 1, 1, 1, which is W, X, Y, Z. Okay, so that's the first step. Once again, you write down the binary number corresponding to each term, and then collect these numbers according to how many ones there are in each of them. And so here is our term with no ones. Here are all of our terms with 1, 1. Here are all of our terms with 2 ones. Here are all our terms with 3 ones. And here's the one with 4 ones. And let's just make sure we have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. And let's go above. 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. So we've now accounted for all of the terms, and now what do we do? Okay, well, I'll say second step. Combine terms appropriately. Now that's of course a little bit vague, but let me show you what I mean. If we we're going to notice that how we've written all of these terms that we have so far in a column, and now we're going to make another column, and it's going to have the same headings for the most part, but it will have new terms in it. And let's see how this goes. Okay, we will look to combine terms from one group with terms from the next group. In other words, we'll look and see if this term can be combined with either one of these, and then we'll look to see if either one of these can be combined with any of these 3. Then we'll look to see if any of these 3 can be combined with either of these 2. And finally, we'll look to see if either of these 2 can be combined with this one. We will never look more than one group ahead. So for instance, we don't have to check and see if this term could be combined with terms down here, or here, or here. Likewise, we won't bother to look and see if these terms, either of these, could be grouped with terms down here or here. That will never happen. If you have grouped these terms correctly, then you'll have a situation where terms can only be grouped with terms one group away. So let's look at this first one, 0, 0, 0, 0 and 0, 0, 1, 0. Well, 2 terms can be combined if and only if they differ in only one location. Now, these 2 do indeed differ in only one location, and that's in the Y position. And you'll get to where you're very quick with this, but for this moment, let's just look and see how this would go. So we have W prime, X prime, Y prime, Z prime, ORed. Now remember, all of these are ORed together, so we're just going to take 2 of those terms that are ORed together, or W prime, X prime, Y, Z prime. And notice that this could be written as W prime, X prime, Y prime, or Y, Z prime, but Y prime or Y is equal to 1, and so this is the same thing as W prime, X prime, Z prime, or excuse me, 1 Z prime, which is the same thing as W prime, X prime, Z prime. So those 2 terms can be joined together, and let's do that. So let me erase all of this so we don't So we'll have room for the rest of this problem. So we're going to combine, now, and keep in mind, I want to also do one other thing here. This is, I'm going to write down the decimal representation of each number. Just, you'll see why in just a moment. So this is 0, 1, 8, 5, 9, 10, 11, oh, let's see, 8, no, this is 13, and this would be 14, and 15. And you'll see why we write these numbers down right now. So we have just seen that this first term will combine with this one to give us w prime, x prime, z prime. So we have w prime, x prime, z prime, and that comes from combining 0 and 1. And it's nice to keep a note of this for future reference. Now, as soon as you've used a term to combine with another term, you want to put a check by it. So I'll put a check by this and a check by the first term. Okay? And now we check to see if this one will combine with the next one. So will the 0 term combine with 8? We saw 0 did combine with 1. Will 0 combine with 8? And the answer is, once again, yes, because this term and the 8 term differ in only one position. That's in the W location. And you can check and see that when you combine these two, you get the W and W prime, they combine to make 1, and you're left with x prime, y prime, z prime. So we have x prime, y prime, z prime, and that comes from combining 0 and 8. Now remember, whenever a term is used in a combination, you need to put a check mark by it. We already have a check mark by 0, so we don't have to put another one, but we do want to put a check mark by the 8. And notice that these are in the no 1 grouping because these are all prime. So if we did, now we won't assign numbers to these, but if we did, it would be 0, 0, 0. We'd have 3 zeros there, 3 zeros here, because they're all prime. So there's no 1s, and that's why these belong together. But that's all the possibilities now. We've looked at this combined with this, and this one combined with this. So that's all the possibilities. And so now we go to 1, 1. And to get terms here, we look and see if either one of these, we check both of these for possible combinations down here. Now, at this point, let me show you a couple of tricks that will make this faster. First of all, when you're looking at combining a term above with a term in the group below, I can tell you immediately there's two things to look for. First of all, if the number, this decimal number, for the term you're looking at above is larger than the decimal number for the term you're looking at below, they will not combine. And secondly, even if the one above is smaller than the one below, if their difference is not a power of 2, then they will not combine. So let me show you how that will go. So for instance, 1 with 5. Now, 1 is certainly not larger than 5, so we don't rule out that possibility on that basis. And the difference between 1 and 5 is 4, which is a power of 2. So these two should combine. And in fact, if we look at 1 and 5, we see that, let me break for just one moment here. Okay, now I see what the problem was. 0, 0, 1, 0 is, of course, not 1. It is 2. And so, let me change that over here. This is 0 and 2. And now let me resume. Okay, so the first term, we're checking this term labeled 2 with the terms down here. Okay, 2 and 5, the difference is 3. So that's not a power of 4, and these two terms should not combine, and in fact they don't, because if you look at this term labeled 2 and the term labeled 5, they differ in more than one position. They differ in the x position, they differ in the y position, and they differ in the z position. So it's no surprise for us that 2 and 5 cannot be combined. Similarly, 2 and 9. The difference is 7. That's not a power of 2. So these two should not combine. And indeed, if you check them, they differ in the w position, and they differ in the y position, and in the z position. Again, they differ in w. They're the same in x, but they differ in y as well and z. So since they differ in more than one position, they cannot be combined. But now 2 and 10, these differ by 8, which is a power of 2, so we expect that 2 and 10 can be combined. And if you look, indeed they can be, because you notice they are the same in the z location, they're the same in the y location, they're the same in the x location, they differ only in the w location. So w will drop out, and we'll be left with 0, 1, 0, which is x prime, y, z prime. So we have x prime, y, z prime. And that's using 2 and 10. And 2 already has a check mark by it, but now we need to put, since we've used 10, we need to put a check mark by it. And again, notice, as we write these down, in each case, the first number is smaller than the second, and in each case, we're seeing that indeed the difference between the two numbers is a power of 2. So that exhausts our checking of this term against all of these, and now let's check this one. Now, what about 8 and 5? 8 is larger than 5, so we don't even need to check it. It will not work. And in fact, if you do check it, you see they differ in the w position, they differ in the x position, and they differ in the z position. And so since they differ in more than one position, they cannot be combined. What about 8 and 9? Well, 8 is smaller than 9, so that's okay. The difference between 8 and 9 is 1, which is 2 to the 0th power, so that is a power of 2. So these two should combine, and in fact they will, because they differ in only one position, namely the z position. So what's left over then when we take away the z is w x prime y prime. W x prime y prime. And that comes from combining 8 and 9. 8 already has a check mark by it. Now we put a check by 9. And what about 8 and 10? Well, 8 is smaller than 10, so it's possible. And the difference between 8 and 10 is 2, which is indeed a power of 2, so those two should combine, 8 and 10. And look at these two and see if you can predict what will drop out. They differ only in the y position, so that drops out. And we're left with w x prime z prime. And 10 already has a check mark by it, so we don't need to put another check. And of course 8 already has a check as well. And this concludes the groupings there of terms from this group with terms from this group. Those are all the combinations. So now I strongly encourage you, we're ready to go to the next one, 2 1s. And I strongly encourage you at this point to stop the video, try to do this yourself, and then resume and see if you got it right. Okay, I hope that you got that right, but before I show you the answer in its entirety, let me show you just part of it, and maybe you'll want to stop the video again. So we need to check these terms with the ones below. And I'm just going to show you all the possibilities. Okay, 5 with 13. 5 is not larger than 13, so we're okay on that basis. And the difference between 5 and 13 is 8, which is a power of 2. So I expect 5 and 13 will work. What about 5 and 14? The difference is 9. That's not a power of 2, so I don't expect that to work. What about 9 and 13? The difference is 4. That's a power of 2. I expect that one to work. 9 and 13. But 9 and 14 I don't expect to work because the difference is 5, which is not a power of 2. Now what about 10? 10 and 13, the difference is 3, which is not a power of 2. I don't expect that to work. But 10 and 14, the difference is 4, which is a power of 2, so I expect that one to work. Now I hope that those are the same ones that you came up with, and that you were able to simplify each of those. But if you came up with something different, review at this point. I would suggest, again, stop the video, review, make sure you got the variables right for each of these, and then we'll look at that together. Okay, so I hope that everything is clear for you now, and now let's go back and write down the the variables for each one. So when we combine 5 and 13, notice that the only position in which they differ is the W position. Everything else is 101. So we have X, Y prime, Z. X, Y prime, Z. And that's 5 and 13, so we put a check by 5, and we put a check by 13. Okay, when we combine 9 and 13, notice that then those two, 9 and 13, differ only in the X position. So the X variable is the one that will drop out, and we will have W, Y prime, Z. W, Y prime, Z after we drop out the X. And again, we're dropping out X because that second bit is the only one in which these two numbers differ. And 9 obviously has a check by it, and as does 13, so we don't have to put any more checks down. And then finally 10 and 14, okay, those differ in the X position, so we have W, Y, Z prime. After we take X out, we have W, Y, Z prime. Same thing down here. After we take X out, W, Y, Z prime. And that was 10 and 14. 10 already has a check. Now we'll put a check by 14. And that's it for that grouping. And so now we'll come to our final grouping, 3 ones. And what we have to do now is look for combinations between these terms and that term. So again, if you want practice, stop the video, take a look, and then we'll all look at it together. Okay, I hope that you concluded that in this term, both of these terms, in this case, both of these terms will combine with that one. So we can combine 13 and 15 because the difference is 2, which is indeed a power of 2. We can also combine 14 and 15 because the difference is 1, which is 2 to the 0th power. And so 13 and 15, they differ only in the Y bit. So what we're left with after we take that away is WXZ. Likewise down here, when we take away Y, we get WXZ. WXZ. And that's 13, which already has a check, and now we'll put a check by 15. And for 14 and 15, they differ only in the Z bit, so that's WXY. WXY. And once we take out the Z term, those two match. And so that's it. We've now gone through all the possibilities for this column. And one last time now, I want to point out that in every case, the first number is smaller than the second number because it'll never work if the first number is bigger. That is, if the higher number has a larger decimal representation than the lower one. And also, in each case, the difference between the two numbers is a power of 2. So now we go again. No 1, Now, at this point, when you're looking for combinations at this stage, I think it's easiest, rather than looking at the numbers. Some people still look at the numbers, but I think it's better just to look at the variables that are present. So, for instance, here we have W, X, and Z. So it definitely could not combine with this, definitely could not combine with this, but maybe it will combine with this one. Let's take a look and see. Well, they both have an X prime, they both have Z prime. The only variable in which they differ is W. One is W prime and one is W. So these two can be combined to give us X prime, Z prime. X prime, Z prime. And that comes from combining the 0,2 term and the 8,10 term. And so I put a check mark by the 0,2 term and also a check mark by the 8,10 term. And again, this 0,2 term cannot be combined with either one of the first two terms here because the variables don't match. Now, what about the 0,8 term? It has X, Y, and Z, so it certainly cannot combine with the 8,9 term or the 8,10 term, but it might combine with 2,10. Let's check and see. Both of them have X prime, and both of them have Z prime. They differ only in the Y position. One has Y prime and one has Y. So since they differ only in one position, they can indeed be combined together to give us X prime, Z prime. And notice that X prime, Z prime that we obtain there from combining the 0,8 term and the 2,10 term, that X prime, Z prime is identical to what we already have. So we don't need to write it down again. And we also don't need to write down the numbers because this says 0, 2, 8, and 10, and if we wrote down these, we'd have 0, 8, 2, and 10. It's just the same numbers, but in a different order. So we've already accounted for that combination. But since we do have it, we want to write check marks by 0, 8, and 2,10. And that's all the possibilities of combining terms here with terms here. So now we go to the next category, 1, 1. And now we'll look for combining terms from this group with terms from this group. Okay, the first one has X, Y, and Z, so it certainly could not combine with either one of these, but what about this one? Well, notice that even though the first term here and the first term here both have X, Y, and Z, they differ in more than one bit. In fact, they differ in every bit, because here we have X prime, here we have X. Here we have Y, here we have Y prime. Here we have Z prime, and here we have Z. So even though these two have the same variables, they cannot be combined together because they differ in more than one term. So we cannot combine 210 with 513 because of that reason, and we certainly can't combine 210 with either one of these because they don't have the same variables. So that takes care of 210. We've checked all the possibilities there. Now let's move to the next one. This one has a W and an X and a Y. So if you check, none of these three terms match that. So it cannot be combined with any of those. Now let's check this last term, W, X, and Z here. So it cannot be combined with any one of these three either. And so there's nothing in the 1-1 term, 1-1 grouping. Now let's look at the next grouping, 2 1s, which would result from combining terms here in the 2 1s group with terms from the 3 1s group. Okay, the first term has the X and a Y and a Z, and that doesn't match anything down here, so no combinations are possible. The next one has W, Y, and Z. That doesn't match anything here, so again, no groupings are possible. This has W, Y, Z, so no groupings possible there, and that is it. So now that we have reached Notice that we don't need to write any more columns. We don't need to go any further because clearly we couldn't combine this with anything here, and there's nothing else below that. So we have done as much simplification as we can, and that concludes step 2. And now for the third step, write all unchecked terms in a vertical column. Okay? So we want to go back to our work here and look at all the terms that are unchecked. Okay, so we have everything in the first column has a check mark by it. When we go to the second column, we see the first one that is unchecked is W, X prime, Y prime. So we have W, X prime, Y prime, and that's 0, that is 8, 9. W, X prime, Y prime is 8, 9. The next one that has no check mark by it is X, Y prime, Z. Which is 5, 13. The next one with no check mark is W, Y prime, Z, which is 9, 13. W, Y prime, Z, and that is 9, 13. The next one is W, Y, Z prime. And that's 10, 14. The next one is WXZ, which is 13, 15. The next one is WXY, which is 14, 15. And the final unchecked term is X prime, Z prime, which is 0, 2, 8, 10. So we have all of these unchecked terms, and let's just to make sure we're not missing anything, let's count them, see if the counts match. So we have 1, 2, 3, 4, 5, 6, 7 unchecked terms, and let's check down here. 1, 2, 3, 4, 5, 6, 7. Okay. So we've written all the unchecked terms in a vertical column, and now let me add one more part to the third step. And all terms of the function in a horizontal row. Okay, now what that means is the following. So here is my vertical column of all the unchecked terms, and now I'm going to write along the top all the terms we had, which were 0. We can get the list right over here. 0, 2, 8, 5, 0, 2, 8, 5, 9, 10, 13, 14, and 15. And from those two collections of information, we make a table. So let me add maybe one more bit to these expressions. So I'll say, then make a table. Then construct and fill the table. Okay, now how do we fill this table? We've constructed the table. Now once again, remember, this vertical column here consists of all the terms that were left unchecked as we went through combining terms here, and the horizontal numbers at the top are simply a collection of all the numbers, these numbers up here, but in decimal form, all the numbers representing the terms in our function. So now that we have this table, how do we fill it? Well, we just look at the numbers that are present in each term and put an X in the appropriate box. So this first row is 8 and 9, so I'll put X by 8 and 9. The next row is 5 and 13, so we X 5 and 13. The next one is 9 and 13, so 9, 13. The next one is 10 and 14, so 10, 14. The next one is 13 and 15, so 13, 15. The next one is 14 and 15, so 14, 15. And then the last one is 0, 2, 8, and 10. And that completely takes care of our table. And then the final step, write down the most efficient expression for your function remember to start with any columns containing only one X. Now, what does that mean? Well, the idea here is that our original function had these terms in it: 0, 2, 8, 5, 9, 10, 13, 14, and 15. So our final expression must also contain all of those numbers. But we can do that by picking from these terms. And we want to do it in a way that is as efficient as possible. Now, why do we start with terms that contain only one X? Well, let's look, for instance, here. This first column has only one X. Why do we want to be worried about that? Well, that tells us, the fact that there's only one X in this column tells us that the only way that we can take care of this 0, which was present in our original function and therefore must be present in our final expression, the only way we can take care of that is through the inclusion of this last term, x prime z prime. So that must be in our expression. So we're going to write down, and by the way, for those of you who are familiar with this terminology, what we're finding here is minimal sums of f of w, x, y, z. And so we'll have f of w, x, y, z is equal to x prime, z prime. We start with that. Now, by writing down x prime, z prime, by including that term to begin with, we have taken care of the 0 term, and the 2 term, and the 8 term, and the 10 term. So we don't have to worry about those terms in their original function at all. So let's scribble out those columns: 0, 2, 8, and 10. Okay? Now, are there any other columns that have only one term, one x? And indeed there is, this one. So this tells us that this term, x, y prime, z, is the only way that we can account for that 5 that is in our original function. So that's the next thing that must be included. By the way, those of you who are familiar with this terminology, these first two terms I'm finding are called the prime implicants. So we have x, y prime, z. That's the 513 term. And by including that one down here in our sum, we're taking care of column 5, but also column 13. And so now we have accounted for terms 0, 2, 8, 5, 10, and 13, and the only columns that remain to be accounted for are columns 9, 14, and 15. And so we have to make choices now as how is the most efficient way to do that. Well, now there's no more columns that contain only one x, so we can't proceed by seeking such columns anymore. We've exhausted all the columns that have that property. But notice that when you look at your remaining alternatives, if you choose this 8-9 term, you only knock out one of the remaining terms that has to be accounted for. The same is true if you choose the 9-13 term. You would only knock out one. Or the 10-14 term, you would only knock out one. But if you choose this 14-15, you'll knock out two terms here. So let's go with that. Let's go with 14-15, which is wxy. So I'll have or wxy. And by choosing that, that eliminates, since that's the 14-15 term, that eliminates columns 14 and 15. And now I have only one remaining term that needs to be accounted for, and that's 9. And there are two different ways that I can do it. And notice that neither one is preferable, because this term here, I can account for this by either throwing in the first term, wx prime y prime, or by throwing in this term, wy prime z, and both of them have the same number of variables, so neither one is really preferable. So this is a situation where we have two minimal sums. And you could choose whichever one you wished. The first one will include wx prime y prime, and the second one would be wy prime z. And what I'm saying here, just to make sure it's clear, although these two functional expressions look different, they are actually exactly the same function. If you look at the truth table for both of these functions, you will see that they are exactly the same, and furthermore, you will see that they match our original function. Now, in what sense are these minimal? Well, they express this function as a sum of product terms in a way that has the minimal number of what are called literals, and those are appearances of the variables. The variables appear 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 terms. There are 11 appearances of the independent variables in each one of these expressions, 11. And notice what a significant improvement we've made, because originally we had 9 terms and 4 appearances in each term. So we originally had 36 literals in this function, 36. and now we've gotten it down to 11. And I stress you can choose either one of these representations you wish. And that's it. That is how the Quine-McCluskey method is used to write a function more efficiently. Okay, so now let's discuss a problem for this material. And we'll have another function of 4 variables, but trust me, I think this one will be a little bit easier. In fact, I'll have to admit, this was the function that I had meant to do in the lecture, but I copied down one term incorrectly and didn't discover it until we were well into the problem. And so I went ahead and did this more involved problem for the lecture, but it's probably good because it's good for you to see in lecture the more involved case, and then for homework to do something a little bit less involved. So anyway, this function is a function of 4 variables, just like the example we did in the lecture, but I think that you'll find out that this one will be a good bit simpler than the one we did for the lecture. So I have here an expression. This is again a function, Boolean function of 4 Boolean variables, and I ask you to circle each one of these that is a valid expression for that. So I'm telling you that at least one of these 4 expressions here is equivalent to G, and possibly more than one is equivalent to G. But you need to circle each one of these that is equivalent to G. And I'll just read all this to make sure the writing is clear. So we have G of W x y z is equal to W prime x prime y prime z prime, or W prime x prime y z prime, or W prime x y prime z, or W prime x y z, or W x prime y prime z prime, or W x prime y z prime, or wxy z prime, or wxyz, or wxy prime z. And the choices are A, x prime z prime, or xz, or wxy; B, x prime z prime, or wxy; C, x prime z prime, or xz, or wyz prime; and D, xz, or wyz prime. And the final thing I'll say is I realize that you can do this with a Carnot map method, but I strongly encourage you to try to do it with a Quine-McCluskey method, because that is what you would want to use with functions having more than 5 independent variables. So that's it, and what I'm tentatively planning to do is for the in-class problem, we'll have another problem like this, but it will be just a function of 3 variables. But definitely don't leave this problem to do the entire problem in class. Try to do it on your own for homework so that you can identify any questions that you have, and then ask those in class, and then I'll give you an even simpler one. As I said, this one for the homework is simpler than the one we did in the lecture, but still you need to try it, and I mean it's not trivial, so try it, and then for the in-class part of this we'll have a problem that's even simpler than this. It'll be a function not of 4 variables but of 3 variables. But definitely try to get this one on your own before class, and then of course you'll be able to check it in class before submitting it. So that concludes lecture 27, and good luck.